so if we were still in school, I would be all like, oh my gosh, y'all, we're on our last chapter and we're almost on notes. But we're not, but I'm still going to say it. This is our last chapter. We only have 3 lesson videos to cover it, and then you'll be done for the year. Alright, so in chapter 11, we focused on the ocean. So we have talked about water pollution before, but in chapter 10, we're going to focus on freshwater pollution, because the problem is we can't drink salt water. So yes, harming its ecosystems harms us because we get food from the ocean and things like that, but freshwater pollution is really devastating because that's where we get our drinking water from. So why is water so important? Well, life on Earth would be impossible without water. All living organisms contain water, and humans are composed of approximately 70% water. The problem is that we have a whole lot of water on Earth, but only about 3% of it is consumable. So if you look, here's all the Earth's water. This light blue portion is all the sea water that we can't consume, and this tiny little sliver is the fresh water, and that's what we can actually consume or drink. So 97% is salty, and then the other problem is there's an unequal distribution, which causes serious regional supply issues across the globe. So it's not like the water is evenly distributed across the areas. Some countries have a lot of fresh water, some countries don't have as much. By 2025, up to 2/3 of humans will live in areas subject to water stress conditions. So again, in chapter 7, we talked about that population growth. If a country is already having a water shortage problem, having more people in that country is just going to make it even worse. So let's talk a little bit of chemistry here. So if you haven't been paying attention all year, I majored in chemistry and I love teaching chemistry, and that's what I know and love. And so I will try my best over the next 2 slides where I actually get to talk about chemistry, not to go into too much detail because I know you don't need to know all of this, but at the same time I'm so excited we get to talk about it a little bit. So the chemical structure of water gives it unique physical properties. Each individual molecule of water, which of course is an H2O molecule, contains 1 oxygen and 2 hydrogens. So H2 means 2 hydrogens, O means 1 oxygen. And they're held together by strong covalent bonds. So don't worry about why it's the shape of a Mickey Mouse head. You'll learn about that later if you ever take chemistry, as to why the hydrogens are, kind of at the top instead of being straight across. You'll also learn why it can't be HHO if you take chemistry or physical science for that matter. And you'll also learn about different types of bonds, but for now you just need to know it's strong covalent bonds. Water molecules are considered polar molecules. So when I explain polarity in chemistry, I always say it's like a magnet. So magnets have a north pole and a south pole. Well, polar molecules, they have a positive side and a negative side. Now, one thing I don't like about the picture is it implies that it has full positives and full negative sides, but it's actually just a partial positive and partial negative. But it's kind of like a magnet, so the molecules act like tiny magnets. The oxygen end of the molecule has a slightly negative charge, and the hydrogen end of the molecule has a partially positive charge. So remember, these aren't full positive and negative sides, they're just partial positive and negative sides. So when it acts like a magnet and has these partial positive and negative sides, opposites can attract. So that's what brings us to hydrogen bonding. Each end of every water molecule is attracted to opposite charges on adjacent water molecules. So if you have the positive side of hydrogen and another water molecule comes near it, it will be attracted to the negative side of that water molecule. So you know how when you have magnets, a north and a south pole will attract. 2 north poles repel, 2 south poles repel, so opposites attract. These strong attractions are referred to as hydrogen bonding. Now, not every polar molecule experiences hydrogen bonding. I feel like I at least need to tell you this. Because if you ever take chemistry, I don't want you to be like, but Ms. Borders in environmental science, you said. Hydrogen bonding is a particularly strong attraction that can happen between hydrogen atoms, which water has, and either nitrogen, oxygen, or fluorine atoms. And so since water also has oxygen, it can experience what we call hydrogen bonding. So hydrogen bonding is responsible for many of the physical properties of water, such as the fact that it has a high freezing and melting point considering its low molecular weight. It has a high boiling point, it has high heat capacity, and it has the ability to act as a solvent. So a solvent just means it can dissolve a lot of other substances. Like when you put salt or sugar in water, it will dissolve it. So enough about the chemistry, although I could go on forever. So how does this relate to our environment? Well, of course, in environmental science, we focus on the hydrologic cycle or the water cycle. So water circulates in the environment. That provides a balance of water in ocean, land, and atmospheric conditions, It renews the supply of fresh water on land. So if we didn't have the water cycle, eventually all precipitation in rivers would take all our fresh water into the ocean, and then we wouldn't have anything left to drink. So what we need is that evaporation portion. Even if ocean water evaporates, the salt stays behind. So like when ocean water evaporates, you don't get salty rain, just the water evaporates, and so then if the clouds move away from the ocean and rain comes down, that's fresh water that can then recharge all the groundwater that we need. And then that's what keeps the rivers and streams flowing and things like that. If we didn't have the water cycle, we would be out of fresh water at this point. So here's just some different types of water that you may hear me reference throughout this video or the next couple of videos for this chapter. So surface water, that's precipitation that remains on the surface of the land and does not seep down through the soil. So surface water could be like a pond or something like that. It just remains there, it doesn't seep down within. Runoff is the movement of fresh water from precipitation and snowmelt into rivers, lakes, wetlands, and the ocean. So runoff is it rains, it runs down into a river, it eventually goes to the ocean. The problem that we've talked about with runoff is as it's running across the land, if it picks up any pollution, it's going to continue that into the rivers, streams, and eventually the ocean. Drainage basin or watershed, that's just the area of land drained by a single river or stream. And then groundwater is the supply of fresh water that is stored in underground aquifers, which are just underground reservoirs. So groundwater is what we pump up into water towers to use for our drinking water and things like that. So, of course, we got to talk about problems that we have with water, because that seems to be what 80% of this class is about, is what are we doing wrong. So 3 categories are too much water, too little water, and poor quality water. You may think, well, why is too much water a problem? Well, that will cause flooding. Too little water, of course, is going to cause people not to have enough water, and then that can cause death from dehydration. And then poor quality water. If you've ever been or heard about a country where you're not supposed to drink the water, it's because they may have water, but it's polluted. It could have microorganisms or bacteria in it that can cause people to get really sick. So it doesn't matter if you have water if it's going to be dangerous to drink. So you need the right amount of water and you need it to be of good quality. So like I said, the main problem with too much water is flooding. So this can occur when a river's discharge cannot be contained within its normal channel. So if too much water is going into a river, it can kind of start to overflow. Or one of the main problems that humans cause is humans remove water-absorbing plant cover and construct buildings in floodplains. So this happens when, of course, we build our cities. So we did have a bunch of trees and grass, so when it would rain a lot, it would absorb a lot into the ground. The trees and grass would soak up a lot of that to keep from flooding. Well, once we cut all that down and we put up roads and buildings, they can't absorb the water. So a lot of it goes into runoff, and eventually it can be too much for our sewers and things like that to handle. So too little water, of course, is a problem. Arid lands, which are also known as deserts, just have a very low amount of precipitation, so they don't have very many plants. So it's not a great place to farm. But people who live there have to eat too. So farmers use irrigation to increase agricultural productivity of arid and semi-arid lands. The amount of irrigated land has tripled globally since 1955, which is a good thing because our population has increased, and so we need more water to water more crops to feed more people. Population growth in arid and semi-arid lands intensifies the water shortage. So if a country already has a water shortage because it's arid or semi-arid, having more people there, which of course is going to happen because we talked about in Chapter 7, our population globally is skyrocketing, we really need it to level off, then that's just going to put even more pressure on that small amount of water that that country has available. So aquifer depletion is a huge problem. So remember, aquifers are just these underground reservoirs. Just think of it as a huge tank of water underground, but the tank is just like the dirt and the rocks. It's not an actual man-made tank. So aquifer depletion results from the removal of groundwater faster than it can be recharged by precipitation or melting snow. So if we're pumping water out of the aquifers faster than it can be replaced, then that's what's called aquifer depletion. It lowers the water table. The water table is just the upper surface of the saturated zone of groundwater. So that's kind of the top portion. It can cause subsidence, which is sinking of the land. So again, think about you have this big, think of it like a cave, and it's full of water. Well, if we pump all the water out, the cave's now empty, and so the land can end up settling or sinking. And then it can cause saltwater intrusion if you live in a coastal area. So again, you have the tank of water, it's the aquifer. If we pump all the water out and you live near a coastal area, seawater is going to go fill that void area. And so now we have salt water where we need fresh water. So that becomes a problem. Because plants and things like that, just like we can't live off of salt water, plants and animals can't live off of salt water either. So it just becomes a problem for everybody. Alright, so we're going to stop here for this lesson video. And so hopefully you will watch the last two and then we'll be done for this year.